Welcome back. In previous videos, we studied convergence tests, alternating series, and absolute versus conditional convergence. Now, we begin one of the most important topics in calculus, power series. A power series is an infinite series that contains powers of the variable x. The general form of a power series is shown here. The coefficients are constant and variable appears with increasing powers. A power series behaves like an infinite polynomial. A power series usually does not converge for all value of x. Instead, there is a region where the series converges. This region is determined by radius of convergence. The series converges when the distance from x to center A is less than the radius r. This gives the interval convergence. However, the endpoints are a special case. We must check them separately. To find the radius of convergence, we usually use the ratio test. We compute the limit of the ratio consecutive terms. Then we determine where the limit is less than 1. Inside the radius, the series converges. Outside the radius, the series diverges. And the endpoints must always be checked separately. Now, let us find the radius and interval of convergence of this power series. We apply the ratio test. First, we write the general term. Then we compute the ratio of consecutive terms. After simplification, the ratio becomes x divided by n plus 1. Now we take the limit as n approaches infinity. The limit becomes 0. Since 0 is always less than 1, the series converges for every real number. Therefore, the radius of convergence is infinity, and the interval of convergence is all real numbers. Since the interval is infinite, endpoint checking is not needed. The power series is very important because it represents the function e to the power of x. Now consider the geometric power series. Again, we apply the ratio test. The ratio of consecutive terms becomes the absolute value of x. For convergence, this quantity must be less than 1. Therefore, the radius of convergence is 1, and the initial interval is from -1 to 1. Now we check the endpoints. At x is equal to 1, the series becomes an infinite sum of 1s. This series diverges. At x is equal to -1, the series becomes 1 minus 1 plus 1 minus 1 and so on. This series also diverges. Therefore, the final interval of convergence is open from -1 to 1. Endpoint checking is very important in power series. Now we are ready to study one of the most important topics in calculus, Taylor series. Taylor series allows us to represent a function as an infinite polynomial. The main question is, can we find a power series that exactly represents a given function? The answer is yes. And Taylor series provide a systematic method for doing that. To find the coefficients of the power series, we repeatedly differentiate the function and evaluate the derivative at a specific point. This process leads to the famous Taylor series formula. Before looking at examples, let us introduce a special case of Taylor series. When the center of the expansions is 0, Taylor series becomes Maclaurin series. In other words, Maclaurin series is simply Taylor series centered at x equal to 0. Many important functions are expanded using Maclaurin series. Because the center is 0, the formulas become simpler and easier to use. For this reason, Maclaurin series is one of the most frequently used tools in calculus and engineering. Let us begin with one of the most important functions in mathematics, e to the power of x. A remarkable property of this function is that every derivative is equals to the function itself. The first derivative is e to the power of x. The second derivative is again e to the power of x. The third derivative is again e to the power of x. And this pattern continues forever. When we evaluate all derivatives at 0, every derivative has the value 1. Substituting these values into the Maclaurin formula gives the expansions 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial and so on. This series converges for every real number. Therefore, its radius of convergence is infinity. And its interval convergence extends from negative infinity to positive infinity. Now let us look at two very important trigonometric functions, sinus and cosine. The Maclaurin series for sinus of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial and so on. Notice that only odd powers of x appears in the sinus series. Now consider cosine of x. Its Maclaurin series is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial and so on. Notice that only even powers of x appears in the cosine series. Both series converge for every real number. Therefore, the radius of convergence for both sine and cosine is infinity. And their interval of convergence are all real numbers. Now let us consider another important example. The function 1 over 1 minus x. This function has the power series expansions 1 plus x squared plus x cubed plus x to the 4th and so on. This is called the geometric series. Unlike the previous examples, the series does not converge for all values of x. Using convergence test, we define that the radius of convergence is 1. Therefore, the interval of convergence is from -1 to 1. However, we must still check the endpoints. At x equal to 1, the series become 1 plus 1 plus 1 plus 1 and so on. This series diverges. At x equal to -1, the series become 1 minus 1 plus 1 minus 1, and so on. The series also diverges. Therefore, the final interval of convergence is the open interval from -1 to 1. This example shows why endpoint checking is an essential part of studying power series. Taylor series and Maclaurin series are among the most powerful tools in calculus. They allow us to replace complicated functions with infinite polynomials. These series are used in function approximation, numerical method, differential equation, physics, engineering, and signal processing, and so on. In this video, we learned the Taylor and Maclaurin series formula. Also, we studied some of the most important Maclaurin expansions. Finally, we discussed radius of convergence, interval of convergence, and the endpoint checking. In the next video, we will study Taylor polynomials and error estimation and learn how to approximate functions with the desired level of accuracy. Thank you very much for watching this video. If you find this video helpful, please like the video, subscribe the channel, and share the video with others.